Okay. Yeah, so I think we can start.
Yes. Okay. So I will. So this is the master's thesis presentation of Rohi Jena, and the presentation will last for about 45 to 50 minutes, and then there will be questions by the committee in the audience. So thank you all for being here, and Rohit, please take it from here.
Yeah. So thank you, Professor Katia. And for everyone here, hello, my name is Rohit, and welcome to my MS thesis talk. In this talk, I'm going to speak about learning mental models of human experts in a search and rescue scenario. And inferring mental models of human can be very helpful in building human robot teams in general. So let's begin. So to build agents that understand how humans function, let's understand how humans form mental models of each other. So humans typically interact with each other without modeling the other person's mind. For example, I don't know what neurons are activated in others or what memories are stored in their hippocampus and the exact model of their brain, but still I can interact with them in my day-to-day life, right? So there is this thing called theory of mind, which is a model of how humans function. So according to the theory of mind, which we will call TOM, a person will take an observation from their sense organs, mostly visual and auditory. And from this observation, they will create a set of beliefs, intentions, and desires. So this belief is basically the state of the world, and intentions and desires are what they want to achieve. And to finally achieve these desires, they perform some action. So this is the forward model. And what we want to do is that given these observations and action, we want to take an agent, and this agent will use this to infer the internal belief state, intent, and desires of the human. So the agent takes this as input and outputs the belief and intentions. Note that this belief may not be an accurate depiction of the real state of the world, and the agent has to figure out by analyzing what actions the human is taking. With this in mind, let's put into perspective the search and rescue scenario. So search and rescue is an amalgam of three broad components. The first component is to form a rescue strategy, because a disaster scenario may have victims of different levels of severity, and they can be present across the layout differently. Secondly, to maximize the number of victims to rescue with an incomplete information, the rescuer must form a navigation strategy to efficiently traverse the map. Thirdly, in a team setting, communication between rescuers is key to avoid redundancy and make use of complementary skill sets. In this talk, we will focus on the first two aspects. So in search and rescue, we want to explore learning-based methods. And in learning-based methods, we typically need a lot of data. And setting up a distribution of artificial disaster scenarios is logistically and financially infeasible for us. So to enable rapid prototyping of such scenarios, what is a solution? Right? So the solution is a simulation to ensure a big distribution of disaster scenarios. And to achieve this simulation, we use Minecraft, which has an open world in 3D. It is lightweight, it is discretized, and it is fully customizable. And with a few mods and APIs, you can customize it to make any disaster rescue scene. For example, you can see the player navigating through the hallway, saving a victim, and navigating across difficult parts of the region in the right. In Minecraft, we will consider 4 types of victims broadly. They are yellow, green, red, and white, and they represent critical victims, less critical victims, expired victims, which are basically the yellow victims that pass away after a certain point in time, and the white victims are victims that are rescued. And we will go into more detail later on. And although the actual texture of these blocks may be different, but the colors are an effective guide to what we will do next. Now, for visualizing the behavior in a 3D setting, it is very challenging to do so. Simply fast forwarding the videos may be challenging for visualization purposes. Therefore, we build a mini grid environment for top-down 2D projection of the Minecraft map. So, and this environment supports different types of blocks. So we can effectively map from the Minecraft to the mini-grid environment. And you can see there are doors and goals, which can be victims in our case. There are walls and so on. So I'll go through the contributions of our work. So the contributions are as follows. So first we'll propose sequential models for rescue and navigation strategy prediction. The key here is to choose suitable representations that consider a full sequence, and not just a particular state at time t. What I mean is that humans are generally not Markovian in nature. So using such an assumption may be very harmful in terms of prediction accuracy or overall accuracy. And so the model should be robust to changing layouts, and we should be able to create models that learn in both small and large maps. So what we can do is we can do some transfer learning from small maps to large maps. This saves a lot of data collection effort, because collecting data is a very challenging process in a search and rescue scenario. And finally, we try to explore generative models for trajectory generation. So the idea here is that regardless of this effort, collecting huge amounts of data is very difficult. And there are also a lot of factors like inconsistency in player strategies, individual differences within players. And so to encompass all these variations, we want to have a generative model, which we will use imitation learning to generate. With this, let's move on to the first part of the talk, which is predicting human navigation and rescue strategies. For this setting, we will use this map layout. This map is nicknamed Sparky, and this map has 18 rooms, and 18 rooms, 3 hallways, and each person is given 10 minutes to complete their mission. There are yellow and green victims hidden throughout the map. So let's talk about the task formulation. Navigation and rescue strategy can entail a lot of things, and we have to restrict ourselves to a more tractable definition. So for the rescue strategy, we consider 2 strategies. So there's a priority-based strategy where the yellow victims are saved first, and a first come first serve strategy where any victim is rescued as we see them. And since we saw that different victims had different rewards, we will have these 2 modes of strategies in our trajectories. So for example, in this case, there is a yellow victim and there's a green victim. And depending on the player's preference, they might ignore this green victim or save it as well. And part of the belief inference also will include whether the player saw this victim or not in the corner. For the next room prediction, so for the navigation prediction, we only confine to a next room prediction in this case. And given the history of the rooms that are visited by the player and the player's inferred rescue strategy, we would want to predict what room they will go to next. For example, here, if they know that there is a green victim in this room, they may not enter this room even if it's closer to the player. We also have a human observer baseline, which is basically human theory of mind observers. So what they will do is they have the same prediction task. So they will also predict a rescuer's navigation and rescue strategy. And they can also choose among alternate beliefs and intent from a menu that they are given. And for this study, we choose 50 Amazon MTurk participants. And we compare these human theory of mind observers against the machine Tom models that we will propose in the next slides. So for the rescue strategy, we need a neural model that considers the entire sequence of messages that we get. So the input to this neural model will consist of the color of the victim, the XYZ location of the victim, and the event that has happened with the victim. So by event, I mean, did the victim enter the field of view of the player, or did the victim get rescued, or did the victim exit the player's field of view? And some more metadata which can entail time steps and all. So now these messages will mostly occur at irregular time intervals. For example, if you enter a room and see a yellow and a green victim close to each other, the player will sort of see them at the same time. Versus if the player just rescued a victim and the next victim is in the other room across the hallway, then the player will take a long time to see that other victim. So there is a lot of irregularity happening in these input messages. So we need models that can basically take into account the irregular time intervals. And we consider 3 models. So the first is RNN-DK, there's RNN-OD, and there's time to wake. And we will go into each of these in slightly more detail. So the idea behind RNN-DK is that in the standard RNN, the hidden units do not change in the time between messages. For example, if you see this diagram, can you see my mouse? No, I think.
Yes.
Oh, you can see the mouse? Wait.
Can I move on?
Yeah, I'm moving it.
No, we're not
No.
able to see it.
Okay.
We can see the mouse. Oh, yeah.
That's fine. So you can see that the hidden units change with time. So these vertical dotted lines are messages that come at irregular time intervals. And you see within these intervals, the hidden units do not change. They are constant. So we want this to change to accommodate various time intervals. So the RNN-DK, what they do is they basically they decay the hidden inputs with time. So this follows the equation dh by dt is basically minus k times h, which is a decay function. And this is how it looks. Finally, the OD-RNN takes this a step further by saying that, okay, we won't decay it, and the dynamics will be governed by a learnable function f theta. And we will learn this f theta to maximize our prediction accuracy. And this is how it looks for some hidden units. You can see that different hidden units follow different dynamics. Finally, we'll discuss the time to wake baseline. The idea behind this baseline is that we want to include time as part of the input. But scalar representations of time are very hard to learn because they arbitrarily go out of distribution because they grow linearly. So we want to have some representation that can sort of loop back. And for that, what we use a vector representation. So this is the representation that we use. So the first index of the time to wake is a scalar representation, but every other index of this vector is a sinusoid. And this has some benefits. So the first benefit is periodicity. So if there is some cyclic behavior happening in the sense that you go to every other room in some time interval, then the sinusoid terms can capture this behavior. And there is invariance to time rescaling, which means if you scale all the time tau with some value, then you can find equivalent amount of omega and phi, which result in the same vector. So this is with respect to the rescue prediction. And for next location prediction, we will use the sequence of areas visited by the rescuers as input. And the output will be the next area segment that the rescuer will visit. So we manually segment the layout of the map into different rooms, and our prediction will be the next area segment. And we use the commonly used transformer architecture for this. So because it's a whole sequence, we want to attend to some parts of the sequence and not others. So this is how it looks like. So I won't go into the details, but the inputs are basically the sequence of rooms that are provided. We calculate some embeddings for them. We pass them through multi-head attentions, and then we get some output which we use to classify. And we use 2 layers of this transformer, and each layer contains 2 heads, which basically means we parallelly compute 2 different embeddings and concatenate them. So given these MTOM baselines, we now compare the performance of the human and MTOM baselines. So here you can see that both in triage strategy and next location prediction, the neural sequence models perform better than the MTurk theory of mind observers. And this is very interesting because we can show that for a small layout, we are actually able to capture more information than human observers. Because human observers tend to forget what happened, like they rapidly forget what happened before. But our models can capture using attention these features. And among the baselines that we had proposed for triage strategy prediction, the time to Vec produces the best accuracy. And I think this may be because of the flexible nature of the vector embedding that allows us to capture more complex representations of how the victims are triaged one after the other. So the main takeaway from this project was that for small maps and few types of victims, predicting simple rescue and navigation strategies work. And however, when we try this on a bigger map, it doesn't scale very well. Maybe this is due to the quadratic increase in size when we increase the size of the maps. And so to do that was to basically tackle that, we tried to transfer representations from these smaller to larger maps, because we know that these prediction tasks work better on smaller maps. So can we transfer these representations to larger maps? And that brings us to the next part of the talk, which is transfer learning in triage strategy prediction. So in the previous part, I talked about the Sparky map, which had some odd 18 rooms and so on. So this is the Sparky map. Now we have the Falcon map, which looks bigger. And so if we compare the Sparky and Falcon maps, Sparky has 18 rooms and 3 corridors, and Falcon has around 24 rooms and 5 corridors. It has more victims, and area-wise, it is 4 times as big as Sparky. So it already looks like a tougher task. And the layout is also slightly more complicated in Falcon, as you can see. And here our goal is to reuse the trajectories from the Sparky map to transfer those representations into Falcon map. So let me define the problem a little more clearly. So in the Sparky map, we have 2 types of victims, yellow and green, and we will have 2 triage strategies. The first strategy will be strict, in which we triage yellow victims in the first 5 minutes and green victims in the next 5 minutes. And we have the preemptive strategy, which is the first come first serve, where you triage every victim in the first 10 minutes. So this follows the Sparky task. And now we have the Falcon task, where we introduce a purple victim, which has a lifespan of 7 minutes. And since we have 3 types of victims, our triage strategy the number of triage strategies will increase. So strict is very similar to the ones we defined above, but here we will triage purple victims from 5 to 7 minutes. There's the preemptive, where we save everyone in the first 10 minutes. There is slack, which is similar to strict, but the yellow and purple victims are clubbed together into one in terms of priority. And then there is the probabilistic, which is based on an expected value of victims that the rescuer can save. So if I have saved 6 victims and there is 1 victim to save in the next 8 minutes, I'll probably not save them right now. And this is the Falcon task. And our idea is to transfer representations from this Sparky to Falcon. So let's talk about parsing the field of view of the rescuer this time, because the previous input format, when we try transfer learning with the previous input format, it doesn't work. And I think it's because different XYZ distribution leads to distribution shift between the Sparky and Falcon, because there is a huge difference in the layout. So XYZ locations in Sparky do not map semantically to XYZ locations in the Falcon map. So we need a layout agnostic input. And to do that, we will basically parse the field of view instead. So to do this, we need to parse the field of view. And the problem with field of view is that it is a variable size. Depending on what the player is looking at, the FOV may have a different shape. So if I'm looking at a wall, my field of view is very limited. versus if I'm looking at an empty hallway, my field of view is very large, right? So we need to take care of this variable visibility of the field of view. And to do that, we need an input size agnostic feature. So what we do is we take attention to merge the variable size of the input and then apply an LSTM in a sequential manner. So this is the core idea that we want to apply. So consider this input FOV, which is a list of block types and their relative XYZ locations. So this list may be of variable size because the field of view is of variable size. And we pass this through the attention layer defined before. And what this does is it creates embeddings for each of the blocks separately. And then we take the average of all these blocks to form a ZT, which is a context of this field of view. Right. And taking this ZT, we do this for every time step. So we will have a ZT minus 1, ZT minus 2, and so on. And finally, we will use this as input to the LSTM. So the ZT is a context containing the summary of the field of view at each time step. And then we pass this through a sequential model to obtain outputs YT. And this YT is basically our triage strategy prediction. And we will finally use cross entropy to train this network. So moving on to the experiments, we use up to 80 train trajectories and 20 validation trajectories from each strategy. And this is done in Falcon and in Sparky. So for the first experiment, what we do is we train with n number of Falcon training trajectories and see the validation accuracy. And you can see this plot. So the x-axis is the number of trajectories used for training the Falcon triage prediction. And it's a no-brainer that the accuracy overall increases with the number of training trajectories used. And with 50 trajectories, there is a 73% accuracy. And with 80 trajectories, there is close to an 80% accuracy. Note that a random classifier would have an accuracy of 25% here because it's a 4-way classification. Once we train with the Sparky trajectories and just fine tune with the Falcon trajectories, we already see a dramatic improvement. Even with a single trajectory, the accuracy shot up to 49.4%, which is close to double of the initial baseline. And the performance with 50 trajectories surpasses the best performance without fine tuning. So the transfer learning basically works very well in a triage strategy setting. So the key takeaway here is that transfer learning from smaller to larger maps does improve performance in a scenario like this. And since it is easier to collect trajectories from smaller maps, we can ideally collect a lot of these trajectories and develop a curriculum and design a curriculum for the network to learn. However, we are still limited by the number of trajectories. For example, in the last experiment you saw, we used up to like 50 trajectories, which is not too many compared to traditional ML algorithms, what they do. So to tackle that, we need a generative model of trajectories, which is a policy. And to do this, we need to explore imitation learning. And that is where the last part of the talk comes in. So this is augmenting Gale with behavior cloning. If you don't know either of these terms, we will explore them. But these are basically two imitation learning algorithms. So, so when we talk about policy and imitation, let's first try to define what a policy is. So a policy is typically just a function that takes a state as input and returns an action or a distribution over actions. And an expert policy, like we saw in the expert trajectories till now. So the expert policy is accessible to us in the form of trajectories, like in this case. So we only know where the car has gone or where the rescuer has been to in terms of rooms. Right? So the expert is just a set of trajectories. And by imitation learning, we want to recover a policy that attempts to learn how this expert behaves. So once we have a policy like that, we can rerun that policy on our maps and we can get more and more trajectories to play around with. And this is the goal of imitation learning. So now that we have set the ground, we will explore a couple of imitation learning strategies. So the first method is behavior cloning. And behavior cloning is a supervised approach to imitation learning, where the policy is trained to simply minimize the error between the action that it took and the action that the expert took. So basically, you take this loss function between pi of s, which is the policy, and the action taken by the expert A, and you minimize that. Seems very simple. However, there is a problem due to this simplicity, and that is the problem of compounding error. So imagine that there is a tiny error in the first state action pair. So the car moves to a state slightly away from the expert, and then it moves away a bit more. And the problem here is that at this location, there is no expert data to guide us back. Like we do not have any expert which goes out of the road, right? So once we drift out a little bit, the actions get farther and farther from the expert actions. And here the actions can just get random. So you see from a minor drift, the car can get out of the road very, very easily. And as it drifts farther and farther from the expert, the actions can get random and there is some drift happening. So the policy slowly drifts away from expert. And what to do here? We don't have any training data. I mean, ideally we can collect training data, and that is what a couple of works do. They iteratively collect data in these regions and try to steer this back, but this is very inefficient. So the second method is a popular adversarial method called Gale. And what they do is Gale trains a discriminator with this loss. So the discriminator is trained to distinguish the expert from the policy that we are trying to learn. So given some trajectories from the policy and the expert, the discriminator will tell which one is which. And using this discriminator, we will train a policy from this discriminator by using the reward function from the discriminator. So we define a reward which is proportional to D, and then we use that as reward for the policy gradient term. And now the question is, what happens on distribution drift? So let's explore this part. So let's say there is still some distribution drift happening here, right? And now you see that when the car comes out of the road, the discriminator can very easily discriminate this state versus the expert state, right? So the reward will be minimized at this location, and the agent has to still recover high rewards. So what does the agent do? So the agent has to come back. So the agent is missing out on states with high reward, and therefore it has to come back to this expert policy to gain more rewards. Because if it drifts out, then it doesn't get any more rewards. So it has to drift back. So the policy will eventually find its way back to high reward states. So you see that Gale kind of tackles this problem of compounding error. Now let's briefly talk about the differences between BC and Gale, and that will motivate our method. So behavior cloning is a stable algorithm because it is just supervised learning. It just takes errors, so it's very stable. On the other hand, Gale combines two of the most unstable algorithms, which is the RL and GAN objectives. Behavior cloning is very sample efficient in terms of training epochs because there is no stability issue. It trains very quickly. And since Gale is as bad as RL objective in terms of environment interactions required, and there is instability due to GAN, so it takes a while to converge. However, behavior cloning suffers from covariate shift due to these compounding errors, as we saw before. So there is some distribution shift happening between the expert and the policy. While Gale learns to get back to the expert state occupancy distribution, and it doesn't suffer from these compounding errors. Finally, the performance of behavior cloning is suboptimal with respect to the expert performance, and with Gale, the performance is optimal with respect to expert trajectories. So you see that they have complementary benefits and complementary problems. So you would ideally want to sort of combine these two methods, right? Now you may wonder, why don't you just pre-train your network with behavior cloning and then fine tune with Gale, right? But it doesn't really work. Empirically, a few independent sources also verified that this method doesn't work. There is also some literature suggesting that warm starting neural networks or pre-training neural networks may converge to suboptimal solutions, although they take less time to converge if the training objectives are hugely different. So this motivates our proposed method. And what we do here is that why don't we consider behavior cloning as an additional source of reward, right? So we rewrite the behavior cloning term as such. And this looks like a policy graded objective, which is a log pi of a times some reward. And the Gale reward is also given as log pi of a times some advantage function. And what we do is we simply take the weighted average of these two terms. So there is this hyperparameter alpha that comes in, and we train our policy with this loss function instead. So a natural question arises, how do we choose alpha, right? If you choose a higher alpha, then, I mean, what do you choose a higher alpha or do you choose a lower alpha, right? So if you choose a higher alpha, if you remember, the alpha is the term for behavior cloning. So the behavior cloning term will dominate. And although it will learn fast, but it will have these overfitting and compound shift problems. If you have a lower alpha, you will have asymptotically optimal performance, but you will have very slow learning. However, the observation here is that you need high values of alpha only in the beginning of the training. So what we do is we anneal the value of alpha from a high to low value. So we start with 1 and we gradually move towards 0. And so first we show some results on Mujoko, which is a continuous control environment. And why we show results on Mujoko is because it's a widely accepted community environment. We start on this first and we'll move to other environments soon. And we also compare with some other baselines. So the reward curves indicate very strongly that our method converges to the Gale reward much faster than Gale itself. And other methods perform inconsistently in terms of optimality. Like sometimes they are optimal, sometimes they are not optimal. So they are very inconsistent, but our method is both consistent and not very unstable as well. We do some ablations on the value of alpha. And we see that if there is a more dominant behavior cloning term for a larger alpha, this leads to more overfitting. So you see the light blue curves are basically with a very high value of alpha. And you see that in this case and this case, the rewards are actually lowest. To motivate the use of this method on navigation prediction or navigation environment, we run this method on grid worlds of increasing sizes. So we have an 8x8, 10x10, and 12x12 grid because these are good toy environments to start with. And the task in this environment is to pick up a key, unlock the door, and go to the goal. And here also you can see that our method, which is in red, performs optimally in terms of success rate, and it does so very fast. And with other methods, you can see that the performance drops very quickly as the grid size increases, but our method still performs better than Gale. Finally, we show some results on like a high dimensional state space. So we consider the car racing environment, which you saw in the beginning. So in the car racing environment, there are 4 stacked images of 84x84, and that is used as the state. And here you can see that our method is performing the best, and with a comparable performance, behavior cloning has a comparable performance. And this is because this environment doesn't need a lot of sequential learning. You can just use the current state to perform greedily and you will perform just fine. And our method basically leverages the behavior cloning's fast feature learning to outperform other baselines in less than 10 times the number of environment interactions. So you can see our method quickly jumps up to this reward value, and the other methods kind of hover around. So to conclude, we start off with predicting navigation and triage strategy in the Sparky map, which is a small grid world map. And we perform better than human observers, which is good, but we still fail to scale up this method to bigger environments. So to address the scaling issue, we explored transfer learning from Sparky to Falcon. And although this works very well and it can be generalized to a curriculum, we still need a lot more trajectories. And to solve this, we explore the imitation learning paradigm. And we explore Gale and behavior cloning, which are 2 imitation learning algorithms with complementary benefits, and we try to combine them in a novel way. This thesis has been the content, like I have received support and a lot of feedback from all these amazing lab mates and colleagues. And this thesis wouldn't have been possible without them. And this brings me to the end of the talk. And I can now take questions.
Great. So first we will have questions from the committee. So Chanyu, would you like to start?
Yeah, so Rahid, that's a very organized and great talk. I have several questions about the second part of the talk, especially on page 27. I'm a little bit confused by the graph.
Just a second.
Yeah.
Yeah, okay.
Yeah, so if there's no fine-tuning, why we can see that orange curve is still growing with respect to the number of trajectories for fine-tuning?
For fine-tuning, so with and without, so the orange curve here is without fine-tuning, and okay. So let's say you have two trajectories from the Falcon map, right? And that is basically the 31.38, whatever. Once you have 10 trajectories for the Falcon map, you have 37.77. And the x-axis is basically the number of trajectories you use for training the Falcon, for training in the Falcon map. So I'm not sure if I understood your question properly.
Oh, yeah, that's basically what is so your horizontal axis is the number of trajectories for fine-tuning.
Right.
And so are those trajectories used not only in fine-tuning, but also in other way that improved the orange curve?
Oh, okay. I think by fine-tuning here, I would mean fine-tuning from scratch. Like when I say the orange curve is, you take a random neural network and you train it on 30 trajectories or whatever. And the blue curve is basically you train it on Sparky first, and then you fine-tune with 35 trajectories from Falcon.
I see. So I see.
Yeah. Maybe the wording isn't a bit clear in the presentation, but yeah, that's what we do basically. So we see that when you train with Sparky first, and you use that as an initialization for the Falcon training, then the accuracy basically shoots up a lot.
I see. Can you give us a rough estimation, like how much like a time reduction with respect? Yeah. So if you have this transfer learning.
Right. With respect to time reduction, I did not have very comprehensive experiments. Like from, if I can just eyeball it, I can say that the blue curve took less time to converge because the number of epochs that it took to like achieve the highest validation was anyway very low. And with the orange curve, these are basically the best accuracies that I had. Like a lot of them actually failed. Like a lot of them had stuck in poor optima, and I did not include those results here. So the orange curve is the best performance that you can see. So if you talk about like time it took to train the best model, it was it was more of a hit and miss for the orange curve than the blue curve.
I see. Yeah, and another question is, what is the key feature of the environment that is necessary for you to make this transfer learning work? So is it required that the environment needs to be this grid world, or it can be transferred to other world?
I think if it's a grid world with different layout, I think it's still very much plausible. But if you, let's say, try to take this from a grid world to something very different, like, I don't know, let's say some image, it is obviously not going to work. But I think this will work with, let's say you introduce a new type of block, right? Let's say you introduce something like a lava block or some other kind of block, then I think it should generalize fine. Because we are using our attention model, then the attention model should ideally learn to pick up these new blocks if they are useful, right? That's why we use this attention mechanism in this project and not something else.
I see. Cool. Last question. So have you, for the last piece of the work, behavior cloning plus scale, have you thought about what if your expert demonstration is suboptimal? Is there any approach to get around that kind of suboptimality?
Right. So when you talk about expert suboptimality, right, that has to be with respect to some reward function that the expert is suboptimal to, right? Like if you, like if the task is to, like, let's say, cook something, right? So, and you say this is a suboptimal dish that you made, right? That is with respect to some reward, which is, let's say, some expert chef's recommendation, right? So when you say something is suboptimal, then either you can have a reward function which says how suboptimal this is, right? Or you can maybe manually pick out the regions where the expert was behaving suboptimally, and then try to, you know, incorporate that information into the policy. But I think it's very domain dependent. Like in navigation, maybe you can pick out in a certain way. In Mujoko, maybe it works in certain different ways, right? So I don't think I have a silver bullet for this problem, but I think it's very domain dependent.
Mm. Yeah, I thought about this problem is that I think in assist project, human can receive some guidance on how to behave more optimally. Yeah, and then that will require your learned model to identify whether this demonstration or this current trajectory is optimal or not. I think that may be an interesting problem to think about.
I see.
Mm.
Yeah, with respect to navigation, there is some sort of optimality that you can achieve. And I think, like, for example, if you try to loop around, that's very obvious suboptimality. If you loop around in rooms that you know there is nothing in, right? So, but yeah, in navigation, I can definitely see some suboptimality detection, right? And yeah, maybe we can include that to improve the assist-based policies, the policies for the assist project. Yeah.
Mm-hmm. Cool, great. That's all my questions. Thank you.
Okay. So Wenhao, you have.
Yeah, Rohit, thanks for the presentation. It's very well motivated and I like it. So I just have a few clarification questions. So given we're already on this page, I just want to ask, so in this training phase for the transfer learning to work, do you still train on both of the map in the training phase?
During training, I only train on Sparky.
Okay,
like
so you train
in
on
the
the
fine
Sparky.
tuning. Yeah. During fine tuning, we don't train on both Sparky and Falcon. I think that's the part of the thing that we want to show, is that the initializations are different for the same training trajectories. Yeah. Cool.
Yeah, and in the very last experiment, I see your algorithm. Can I go to that slide? I see the comparison of the performance where your curve like just stop earlier than the other methods.
Yeah. Just a second. Yeah. I don't know how to skip through the animations.
Yeah, this one. Yeah, right. So like I don't know if I missed that earlier. Like, have you mentioned about why your curve, like why your profile stopped earlier? Is that because like they will be performing exactly the same for the rest of the like increasing number of environment iterations?
Oh, I think it just stops there and just hovers like, so if you see this red curve, for example, it hovers around some 600 range, right? And our method also kind of hovers around this almost 800 range or whatever, right? And it just basically, in the original plot, it obscured the BC and this thing. It was confusing to sort of visualize. So I just cut it here.
I see. Yeah, because like usually people will tend to show the whole
thing,
otherwise.
But
otherwise maybe missing like whether it will actually converge or stabilize or it will just fall down.
It's stabilized from this point. Like if you can see the mouse, from 300,000 to 500,000, it was stuck at the same reward. So we basically stopped it there, and I tried to plot it for 10 million, 5 million as well, and it just like hovers around this part. So I basically stopped them wherever they sort of stabilize, like wherever they sort of like, how do I put it, like they don't grow anymore. So for example, the green curve still tries to grow a little more at this point. The red curve, I don't know where to stop, so I just kept the whole thing. But the green curve still tries to grow, and that's part of the thing that we want to show is that it takes a long time for Gale to converge, although it does
Yeah,
converge to the optimal thing.
Yeah, I think like if you want to put in the paper in the future, probably it's better to show the whole story and like at least show them in the same time scale. And I think this could show you like first of all your algorithm's like sample efficiency, like you can get the very good performance in a very short of time, and also like you can stabilize. Otherwise, people will have questions like stabilize.
That's why we started off with a lot of these small tractable environments where Gale also converges in a reasonable amount of time, so we can show them like so in the document there are more results. I'm just showing like part of them. So for Mujoko also we had like 5 results here, and for this that's all. And in the ablations we had some more results. But you're right. Okay.
Yeah, cool. So I just have 2 more high-level questions. So first is about the first part of your work where you want to predict the player's strategy. So I was wondering, like, because like you mentioned, human could sometimes go wrong, right? Like they may not strictly follow one particular strategy. Probably they may be short-sighted and deviate a little bit from their current strategy. So in your algorithm, like, are you predicting like with the assumption that human is consistent with its own strategy and predict the best estimated strategy for the human, or you will predict not only this best estimated strategy, but also maintain a kind of distribution of estimating how human strategy is deviating or not, like depending on this different type of assumption on the models. Like basically how robust is your prediction algorithm is? Are you ruling out those outliers, or you're able to automatically fit even if human gradually switch strategies in the same task?
Right, that's actually a good question. In terms of modeling, the modeling is such that you are predicting something at every time step, right? So if the human changes their strategy in between, so the agent can ideally predict this since we are predicting at every time step and not making like a set in stone prediction. Like we can potentially change our prediction at every time step if we wish to. Having said that, we did not have enough trajectories where humans showed this kind of variance. Humans mostly stuck to the yellow first, which was the strict strategy where they saved all the yellow ones first and then the green. So we had a lot of data skew there as well, but still we could reasonably predict the triage strategy. But like theoretically speaking, we can do this, but we didn't have enough data to like sort of, or we did not have any consistent data where the human was consistently changing strategies after the point, and then so I would say we did not have conclusive evidence in that area.
Yeah, I was asking because even if you're able to predict at every time step, the historical data may be noisy, or like even eventually like switching the strategy for the humans. So that's why, it's kind of like interesting.
Yeah, the data was noisy, but the humans were more or less like inclined towards this yellow first strategy. So we didn't see a lot of variance there, but we still saw that like, we did not have enough data to sort of create a new, not new, but like sort of make this, sort of have data where you have one strategy for this time and then a new strategy for this other time. If we had, we could have tried our algorithm and like seen what kind of behavior we get. But
yeah, sure, thanks. So the last question would be like regarding the scenario. So if I understand correctly, for now you just take observations from the human and then infer the predicted strategy, for example, the next location of the room human is going to visit. So I was wondering, like, have you thought about like if you have like a robot working with human together, like how the robots would be able to communicate to, so like is there any multi-agent architecture here that deal with this different information from different agents and then somehow merge their knowledge together to help better prediction or help give guidance to a human? Is that like part also of your problem, or this is not, has not been addressed?
We haven't delved into it like very deeply. So in the last couple of months of my work, I was diving into the multi-agent aspect of it. So where we have, let's say, 3 players now, and each of them have some complementary skill set. And now the task of the agent is to sort of make sure that these humans don't perform redundantly and sort of coordinate well together. But could not include this in the thesis due to, like, we don't have any too strong results yet to show in the thesis. But this is something that I have been, like, I have started to work towards, and maybe I'll explore it more.
Yeah,
I
sounds
think this
great.
should be possible. Yeah.
Yeah, cool. Yeah, thank you. That's all my questions.
Okay.
Okay, so that's great. And I don't have any questions. I just want to say that that Rohit is starting to model, as a matter of fact, the beliefs of the players in this team, and the team performance, the team thing that we have now. And also they have, when he says complementary strategies, they have different complementary capabilities. They have different roles. So in this new scenario, we have a bigger map, and they can take roles like the medic, and there is rubble now. And so the rubble person needs to clear the rubble before, if it's rubble in front of a room, for example, then rubble needs to be cleared for the medic to go and triage, for example. And then there are other roles. So this is much more complicated because there are preconditions, right? So it's not just a matter of strategy, but now the one could satisfy preconditions for the other. And the agent has to predict all that. And then in the next step, it would be for actually this intervention that we're talking about, when, how, in terms of advice. And when do you give advice, and to whom do you give advice? And there are different levels of advice. I can give advice to one player, or I can give advice to the team as a whole. And what does that mean to give advice to the team as a whole now? That's a big issue, I mean, to think about and to model. And so there's a lot of future work.
Yeah, I can see that. Yeah, it's interesting to close the loop, where not only predict, but also use that to do something.
Yeah, exactly.
For human, yeah.
So that would be great. So yeah, so now we can open it for questions from the audience. If there is anybody that has any questions, please speak up or raise your hand or whatever. Please speak up if there are any questions. Okay, so if there are no more questions, then we thank the audience and excuse them, including Rohit. And Rohit, you may want to make me the host now.
Oh yeah. Okay.
Please stop
Yeah.
the recording. Yeah.
And
Yeah,
stop
just a
recording here.
Please stop the recording.
Right. Just a second. Okay. Yeah, it's actually, yeah, it stops my. Just a second. Yeah, the problem is that I can't see the mouse. So
Okay, just like,
now I can.
yeah,
Yeah, now I
stop
can.
the sharing.
Yeah.
Got it. Yeah. Okay.
Did you stop?
Yeah. Oh, the recording. Yeah. Just a minute.